So we're talking about an elevator. Now, kids, an elevator is really, in physics, it's basically an Atwood machine. And since you've talked a lot already about vectors, right? Acceleration vectors or force vectors, okay? We can think about it either way. If we reconcile vectors, it's very, very simple to see how an Atwood machine or a basic elevator works, okay? Now, the first thing we started out with was, if this is a pulley, and right here we have a bunch of kids on an elevator, all right? And it's, there we go, everybody's happy. So, the wire, or the cable on the elevator goes around, and there's an electric motor right here, spooling, and using electricity, and it can spin around in a circle, and as this spins, it pulls the cable down that way, and then the cable right here will move that way. Does everybody agree with that? And we can put multiple pulleys, and that's a different lesson. But we're talking about having a single pulley, and we said, wow, the best thing to do to make this thing have to pull with less force, because the force that we're pulling down here is got to be equal, it's got to be greater than the force that's going down here, right? Right? Only if we can pull down on this side harder will it overcome this force. And what the little bit we have left over will provide the acceleration to go up. Does that make sense? The extra force is the force up. So we've got a down force here that you're doing work. We've got a down force here, natural from gravity. This is just how much this whole thing weighs. So you'll have to pull with more force than the weight of this to get it to move up. Right? And in this situation, let's say this was 10,000 newtons, and you pulled with 10,001 newtons of force, then there'll be 1 newton of force left, and this thing will move up very, very slowly. Do you agree? So we have to pay for this electricity to run this machine. So the simplest thing we could do is to put an elevator on the other side and hope that there's people in it. Right? What if there's 4 people in this elevator? Then we don't have to do any work. We don't have to use any energy or apply any force to get this machine to go down. Does that make sense? So this thing, these people could be on floor 0, and this people could be on floor 10, and the elevator wouldn't have to do any work, use any electricity. This is just naturally going to go down. The only thing they would do is probably apply a brake here when they felt like this was going to be going too fast. Okay? That's the general idea of an Atwood machine. Here is the second idea of an Atwood machine. The second idea is this. You know, we talked about on Earth that if you have a weight, here's a little weight. It's a 1 kilogram weight. It will fall to the Earth at 9.8 meters per second squared. Right? And if you have a 2 kilogram weight, twice as big, and it's on a string and that breaks, it will fall to the Earth with what acceleration? 9.8 meters per second squared, right? Free fall, death spiral, hating it, right? Okay, well, what if we had, I'm just simplifying this, a 2 kilogram weight on this side. No, I'm drawing it backwards. What if we had a 1 kilogram weight on this side and a 2 kilogram weight on this side? Doesn't that mean that this side has 1 kilogram more weight? right? So would this situation be the same as this? Here's the pulley, right? Here is a 1 kilogram weight, and here's a person holding it, right? Now, are these two the exact same situation? Let's say this person lets go. Is this the same? A 1 kilogram weight and nothing on this side compared to a 2 kilogram mass and a 1 kilogram mass on this side? Are these two the exact same? Since I'm filming this, I'm trying to keep it short for the kids at home. I'm going to go ahead and tell you the answer is no. This is not the same thing. If you let go of this, what's this weight going to do? It's going to fall to the earth with an acceleration of 9.8 meters per second per second. That's going to fall with gravity, right? But this is different. And the reason it's different is because we're dealing with forces now. We're not dealing, there's no opposing force here, right? So the general idea behind the Atwood machine is this. There is a downward force here. And what is the downward force in this situation? F equals ma. What's the mass? 2 kilograms. And what's acceleration due to gravity, where this thing's trying to fall? We're on the planet Earth. 9.8 meters per second. So there's a downward force here of 19.6 newtons down, right? On this side, opposing this, there's a downward force, F equals ma over here, and this one is 1 kilogram times 9.8 meters per second. So there's a downward force here of 9.8 newtons, right? Now, isn't pulling down on this side the same thing as pulling up on this side since we're going around this wheel? Does everybody agree with that? So really, this thing is no longer in free fall. And kids at home, you can go back and rewind this for a second, but watch what I'm going to do. Really, the whole situation breaks down to this. Nothing matters at all except for you have a downward force here, total of 19.6 newtons. And you have an opposing force up of 9.8 newtons, right? Now let me ask you a question. How much weight, how many kilograms are being moved? What's the total mass? If we remember, there's a 2 kilogram weight here and a 1 kilogram weight here. Aren't both of them moving? So how much total mass is the force being applied to? Yes, the new imaginary block that we have here, this includes the weight on both sides because they're all attached to the same string. So what's the difference? 19.8 down, 19.6 down minus 9.8 up. 19.6 newtons minus 9.8 newtons leaves us 9.8 newtons of force left to go down. Does everybody agree with that? Right? Okay. And there's a 19.6 newtons downward force on this 3 kilogram mass. So force equals mass times acceleration. There's 9.8 newtons of force on a 3 kilograms total of things that are moving. So the acceleration of this thing would be actually just 9.8 newtons divided by 3 kilograms. That gives us like almost, if we round it off, 3.3, right? Meters per second per second. So you're falling with much less acceleration because that counterweight is on the other side. So the elevators don't work in reality on the difference in the weights on each side, well, in the masses on each side. Their total acceleration is due to the difference in the forces on each side and the fact that both of these masses are moving. So you can drive your acceleration down really, really low. And if the weights go up and the differences between them are small, then you can make an acceleration that's very, very, very slow. And people can move safely up and down in counterweighted elevators without using any electricity. That's theoretically how it can always work. If you have more weight on the side you wanted to go down. That's it. That's an Atwood machine.